Hello, in this video, we are going to take a look at 4 examples of using the ratio test. So, the first example is this series n equals 1 to infinity of -1 to the n minus 1 times 3 to the n over 2 to the n cubed. So, the ratio test tells us to look at the limit as n goes to infinity of the ratio of the n plus 1 term over the nth term. So, filling that in, we would have, adding 1 to all of these n's, we would have -1 to the n minus 1 plus 1, it's just n, times 3 to the n plus 1, over 2 to the n plus 1, n plus 1 cubed, all over. And then a sub n is just our sequence as it is, -1 to the n minus 1, 3 to the n, over 2 to the n cubed. Keep, change, flip gives us the limit as n goes to infinity of -1 to the n times 3 to the n plus 1 over 2 to the n plus 1, n plus 1 cubed, times 2 to the n cubed over -1 to the n minus 1, 3 to the n. Things cancel very nicely here. So first, we have a 2 to the n and a 2 to the n plus 1. That will cancel down to just be a 2 in the denominator where the larger number of the 2's is. So 2 to the n over 2 to the n plus 1 comes out to be 1 over 2. And we also have a 3 to the n plus 1 and a 3 to the n. Those cancel to give us a 3. And we have a -1 to the n over a -1 to the n minus 1. These cancel each other out to just be -1, but we are looking at the absolute value, meaning the -1s don't actually affect anything anyway. So not only do they cancel each other out, they completely go away because we don't need to worry about these negatives. And then the things that don't cancel out are the n cubed and the n plus 1 cubed. So there is our nice limit that we have simplified down to. And the nice thing about this limit is it's irrational, with the degree being the same on the numerator and the denominator. We have an n cubed, and in the denominator, if we multiplied that all out, we'd have an n cubed. So this limit is the limit of a rational, meaning I can just look at those leading coefficients and get 3 halves. So we have the limit, and now to use the ratio test, we need to compare this limit against 1. 3 halves is bigger than 1. So by the ratio test, the ratio test says if the limit is bigger than 1, the series is divergent. So the series n equals 1 to infinity of -1 to the n minus 1, 3 to the n over 2 to the n cubed is divergent by the ratio test. So, thinking about sentences, our series converges or diverges by the test with our reasoning. Inside our work, we do need to have that whole ratio test work, but the reasoning ultimately is how does the limit compare against 1? Right, let's take a look at another example. We have the series n equals 1 to infinity of -5 to the n plus 1 over 2n factorial. Setting up our ratio test, we're going to take all of our sequence and add 1 to any n we see. So n plus 1 is n plus 2 over 2 times n plus 1. So in parentheses, we have the n plus 1 factorial. And then we divide by the sequence kept the same. So -5 to the n plus 1 over 2n factorial. Keep, change, flip. This becomes -5 to the n plus 2 over 2n plus 2 factorial by multiplying this 2 in, times, flipping the denominator fraction, 2n factorial over -5 to the n plus 1. Things that cancel. We have a -5 to the n plus 2 and a -5 to the n plus 1. When we divide those, we'll end up with just a -5 in the numerator, as we have -5 to the n plus 2 over -5 to the n plus 1. This is equal to -5. Then we have times 2n factorial. And this 2n plus 2 factorial, to see how it cancels, I'm going to write out a little bit of what that looks like. So 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, and so on, until we multiply down to multiplying by 1. However, you notice this last bit is 2n factorial. So I'm going to just write that as 2n factorial. And that means I have a 2n factorial in the numerator, a 2n factorial in the denominator. So this equals the limit as n goes to infinity of -5 over 2n plus 2 times 2n plus 1. And the only thing that's growing at all is that denominator grows to infinity while the numerator stays fixed, so this limit is 0. Our conclusion, 0 is less than 1, and the ratio test tells us that if the limit is less than 1, the series n equals 1 to infinity of -5 to the n plus 1 over 2n factorial converges absolutely by the ratio test. Taking a look at another example, we have the series n equals 1 to infinity of n times 2 to the n minus 1 all over -7 to the n. Setting up our ratio test, we have add 1 to all the n's, divide by the normal sequence. Keep, change, flip. This limit becomes n plus 1, 2 to the n over -7 to the n plus 1 times -7 to the n over n to the 2n minus 1. Things that will cancel. The 2n minus 1 will cancel with the 2 to the n, leaving us with just 2. The -7 to the n will cancel with the -7 to the n plus 1, leaving us with just a -7 in the denominator, making this limit n goes to infinity of 2 times n plus 1 all over -7 times n. This is a very nice rational that we can take the limit of and look at those coefficients. This limit comes out to be 2/7. It's a positive 2/7 because of the absolute value. And now we compare this limit against 1. 2/7 is less than 1. So our series n equals 1 to infinity, n 2 to the n minus 1 over -7 to the n converges absolutely. Let's take a look at one more example. That last example is -1 to the k plus 1, k to the 2k, k factorial in the denominator. So setting up our ratio test, adding 1 to everything, -1 to the k plus 2 times k plus 1 to the 2k plus 1, and note the parentheses, all over k plus 1 factorial, k plus 1 factorial, and now our sequence as normal, -1 to the k plus 1, k to the 2k, all over k factorial, k factorial. Keep, change, flip. This limit is equal to -1 to the k plus 2, k plus 1 to the 2k plus 2 by distributing this 2 over k plus 1 factorial, k plus 1 factorial times k factorial over -1 to the k plus 1, k to the 2k. Noting some things that cancel. Number 1, we're looking at an absolute value. So not only do the -1s cancel each other to become just a -1, but since it's inside a parenthesis, inside an absolute value, we don't care about them at all. Second thing is k plus 1 factorial is the same as k plus 1 times k factorial, because we would be multiplying by everything as we subtract 1 each time. So these k plus 1s, factorials, are really k plus 1 times k factorial times k plus 1 times k factorial, because we have 2 of them. So the k factorials cancel. And now, one more thing, let's write this out a little bit clearer. Our limit should be with k. I wrote n, as all of our last examples had been n. They should be k. K goes to infinity. of k plus 1 to the 2k plus 2 is all that's left in our numerator. And thinking about what that means is that is k plus 1 to the 2k times k plus 1 squared. And in the denominator, we have a k plus 1 times k plus 1. What is another way to write k plus 1 times k plus 1? K plus 1 squared. K to the 2k. So our k plus 1 squareds cancel, and this long limit has broken all the way down to just being k plus 1 to the 2k over k to the 2k. Some rewriting gives us that this limit is k plus 1 over k all to the 2k. Put that on the side. So our whole fraction is to the 2k since they both share the same exponent. And we can rewrite that k plus 1 over k to the 2k as k plus 1 over k to the k squared. And we can drop the absolute value as we have gotten rid of anything that would be making this negative. Now, this is where the beginning of the first video comes back, because the limit as k goes to infinity of k plus 1 over k to the k is e. So this piece here is e, and we still have this squared, so this limit is e squared. The limit of our ratio comes out to be e squared. We compare e squared against 1. E squared is bigger than 1, because it's 2.7 yada yada squared. So it's going to be something bigger than 1. So our series k equals 1 to infinity of negative 1 to the k plus 1, k to the 2k, all over k factorial, diverges by the ratio test. So there are 4 examples of using the ratio test to tell if a series converges or diverges.